Modern artificial intelligence relies on massive sequences of data to understand language, but processing millions of linguistic variables at scale creates a severe computational bottleneck. For years, the state-of-the-art systems for sequence modeling and machine translation have been recurrent neural networks, specifically long short-term memory and gated recurrent models. Recurrent models have a strict mechanical constraint. To generate a hidden state at any given position, referred to as HT, the network must first compute the hidden state from the exact previous step, HT-1. This timeline graph illustrates the consequence. Because operations are inherently sequential, they form an ON bottleneck, lining up one after another, precluding parallel processing. As the sequence stretches, processing a paragraph instead of a sentence, memory constraints limit batching, and latency severely limits overall performance. To scale language models effectively, researchers needed a way to decouple the analysis of a sequence from the sequential computation itself. In 2017, a team at Google Brain and Google Research proposed a radical solution, a new architecture called the transformer that dispenses with recurrence and convolution entirely. Instead of relying on a sequence-aligned network, the model relies exclusively on self-attention, relating different positions of a sequence to one another simultaneously. By treating sequence data as a matrix where all points can interact simultaneously, this approach reduces the maximum path length between long-range dependencies down to a constant O of 1. The objective is strictly defined: establish global dependencies between inputs and outputs while reducing the number of sequential operations to an absolute constant. Removing the sequential constraint allows for massive parallelization. The resulting models achieve superior translation quality while drastically reducing the time and hardware required to train them. At the core of the transformer is an attention function, mapping three specific vectors, a query and a set of key value pairs, into a final output vector. Looking at this schematic, queries, keys, and values are packed into massive matrices, Q, K, and V, allowing simultaneous computation. The network calculates the dot product of the query with all keys, QKT. This acts as a compatibility function, determining the appropriate weight for each value. This softmax plot reveals a problem. For large DK values, rapid dot product growth pushes the function into flat tails, where gradients vanish, halting learning. By scaling dot products down by 1 over root DK, values stay in the active region, maintaining stable gradients. The softmax function then dictates the weights, and the final output is computed as a weighted sum of the V matrix. While similar in theoretical complexity to additive attention, this specific scaled dot product approach is mathematically identical to highly optimized matrix multiplication code, making it drastically faster and more space-efficient to run on modern hardware. Relying on a single attention function presents a limitation. Averaging all attention weights across a single high-dimensional space prevents the model from independently attending to different representation subspaces. In multi-head attention, initial queries, keys, and values are split and linearly projected h times in parallel into smaller dimensions. The attention function runs on each version simultaneously. Finally, independent outputs are concatenated and projected one last time to produce a single resulting value. Because the dimensionality of each individual head is reduced, for instance, splitting a 512-dimension space into 8 heads of 64 dimensions each, the total computational cost is identical to a single-head attention mechanism with full dimensionality. The model gains the ability to jointly attend to complex linguistic nuances across multiple positions simultaneously without increasing the overall computational budget. This diagram shows the complete transformer structure, featuring an encoder stack on the left and a decoder stack on the right. The encoder comprises 6 identical stacked layers, each containing a multi-head self-attention mechanism and a position-wise fully connected feed-forward network. Around each sublayer, the engineers placed a residual connection followed by layer normalization. The decoder stack uses 6 identical layers as well, but it inserts a third sublayer, performing multi-head attention directly over the completed output of the encoder stack. The decoder must operate under a strict autoregressive constraint. It can only rely on known outputs from preceding positions. To prevent leftward information flow, the first self-attention sublayer masks out illegal future connections by setting their values to -infinity before the softmax function. The dual stack structure cleanly separates the tasks. The left side builds a complete contextual representation of the input, and the right side uses that context to generate the sequence one element at a time, assembling the final output. Eliminating recurrence and convolution creates one final structural challenge. The model currently has no inherent way to understand the sequence order. Without an update, it treats a sentence as a disorganized bag of words. Returning to the macro architecture, the solution appears at the very bottom. Positional encodings are injected and summed directly with the input embeddings before they enter the encoder and decoder stacks. Encodings are mapped using sine and cosine functions. Each dimension corresponds to a unique sinusoid, or relative and absolute position. Since wavelengths form a geometric progression, any fixed offset acts as a linear function, allowing the model to easily attend by relative position. The engineers chose fixed sinusoids rather than learned positional embeddings, so the model could potentially extrapolate and maintain accuracy on sequence lengths much more than those it encountered during training. By mathematically defining the coordinates of each data point, positional encoding successfully replaces the sequential memory of an RNN, preserving the order of language without the bottleneck of sequential processing. Returning to the computational metrics established earlier shows exactly what this architecture achieves in practice. This data maps the structural trade-off. Recurrent layers require O of n sequential operations, but self-attention connects all positions with a constant O of 1. Furthermore, the maximum path length also drops to a constant, making it easier to learn long-range dependencies. This theoretical efficiency translates directly to empirical results. On the standard WMT 2014 English to German translation task, the model achieved a 28.4 BLEU score, beating existing ensembles by over 2 points. On English to French, it established a single model score of 41.8. Those state-of-the-art results were achieved after training for just 3.5 days on 8 GPUs, a tiny fraction of the computational training costs demanded by the best competing models. The architecture definitively proves that massive computational efficiency and superior output quality do not have to be mutually exclusive. Because self-attention directly computes a matrix of mathematical weights between data points, it yields an additional benefit. We can visualize exactly how the model evaluates language. By inspecting the attention distributions, we can see that individual attention heads learn to perform distinct tasks related directly to the syntactic and semantic structure of a sentence. In this Layer 5 visualization, we can observe the model resolving long-distance dependencies. Multiple attention heads prioritize a distant dependency for the verb making, mathematically linking it across the sentence to complete the phrase making more difficult. The network autonomously extracts these complex linguistic rules without requiring structural priors or sequential recurrence. By dispensing with sequence-aligned operations entirely, the transformer successfully executes sequence transduction, relying strictly on self-attention. It removes the sequence bottleneck, establishes perfect global dependencies, and massively accelerates training. For sequence modeling, attention really is all you need.